Our next talk for you right now, How We Ran an Online Hardware CTF by Thomas Hobson, Emily Trau and Tom Nguyen. Let's welcome them to the stage.
Hello everybody, great to see you all. Welcome to our talk, How We Ran an Online Hardware CTF. So our speakers today will be Hexef, also known as Tom, myself Emily, and Dot, or Tom as well. A quick rundown of Down Under CTF. We run an online capture the flag competition, and this year we had over 4,000 players participate in a range of challenge categories, including web, reverse engineering, binary exploitation, and more. For the 5th iteration of Down Under CTF, we wanted to introduce a new class of hardware challenges. For many of our players, this might have been their first opportunity to experiment with hardware security, even if they might otherwise won't have the tools or equipment to do so. Our competition was open to the public, and we welcomed teams from around the world. We are immensely proud of their efforts, and collectively they attempted our hardware challenges over 2,000 times. To facilitate this dream, we needed to first design a completely novel hardware and software stack. We wanted to create a platform of real circuits, allowing us to surpass the limitations of simulation and aim for complete authenticity in modeling threats and attacks. Users would be able to upload arbitrary code for execution, lending them complete control over their virtual hardware lab, all while maintaining the security, isolation, and safety of our underlying infrastructure. Early in the design process, we had to pick the microcontroller that would be the heart of our platform, what the user would be interacting with the most, and that they would upload their code to. For this, we had to evaluate a lot of options on the market, and we tested them against a strict set of requirements. First and foremost, it should have a development environment that is easy to install. We wanted to make this as small of a hurdle as possible. Embedded IDEs don't always have a strong reputation here, and this quickly rules out most of the industrial chip families. Support in Arduino is a must. To help our players in their learning journey, the microcontroller should have an existing development board and large established community resources. We want to aim for something that's already popular with the maker, hobbyist, and education audiences. To maintain the safety and stability of our systems, we need to have a clear view of what is running on the processor at all times with external control and debugging. Unfortunately, this excludes possibly the most widespread family of chips among hobbyists, the venerable 8-bit AVR microcontrollers that are in the Arduino Uno and its relatives. Next, while we appreciate our players for sticking to the spirit of the competition, but being a large CTF with open registration means that we do have to take certain mitigations against bad actors. Malicious code should not be able to permanently modify the behavior of the chip or damage it through setting fuses or writing one-time programmable memory. And finally, many of our options contained wireless functionality. Chips like the ESP32 have been made widely available and affordable thanks to the proliferation of IoT devices and have earned a wonderful loyal following among makers and home automation enthusiasts. Such wireless functionality, if we used those chips, would have to be disabled somehow to prevent us from interfering with the local radio environment. I know we're asking for a lot already, but it would be really, really great if it was cheap as well. Why can't we have that? Even with all of our requirements, we were able to find the perfect chip that ticked every box, the RP2040, otherwise known as the Raspberry Pi Pico. On top of everything I previously mentioned, it sports a powerful dual-core ARM processor, lots of RAM, fast programmable I/O pins, you need those for those precise timing attacks, and a completely stateless design with no fuses or one-time programmable memory. To quote a Raspberry Pi engineer, it was designed to be absolutely unbrickable. At less than $1, it is truly the only perfect processor for our application. This project would not be possible without it. We've picked our microcontroller, but it takes a lot more to transform this building block into a fully fledged system. Passing off to HexF to tell you about our surrounding hardware architecture.
Ooh, is it working? Cool. Hello everyone, I'm HexF, or also known as Thomas. So we're going to kick off with what's the topology of the system. So basically everything around here is centered around the host computer, which is going to talk to a bunch of these managers, which is something we built ourselves. So these managers talk over USB. The managers interact with these runners over SWD, or the Serial Wire Debug Protocol, and UART, or Serial. These runners are then paired with these challenge cards, which are ultimately the things you're attacking with your code that runs on the runners. So this is basically what a challenge card looks like. So we start with all the challenge stuff. This is unique per board or per challenge. Then we get to the edge connector here. So this is a PCIe edge connector. These were picked just because they're really cheap to manufacture. The connectors were relatively cheap. It's also double-sided and gives us enough I/O lines to get both the I/O from the runner up to the card so that we can allocate it how we see fit for each challenge, as well as allowing us to provide power and data on that left side of the card as well. So there's data on the left for challenge management, which in this case, on this challenge specifically, was a ID EEPROM. So this is just a SPI EEPROM that allowed us to identify which card was in which socket. And for other designs, we also put the SPI here directly into an MCU, which also allowed us to do things like releasing flags, giving certain conditions on the card, which allows us to simulate more real-life conditions like you're opening a door. It also allows us to just reset the challenge over SPI nice and easily. I was also asked over Twitter what would happen if I plugged it into SPI, and it turns out your board, the challenge board, might survive, your computer definitely won't. So we'll take a close look at the manager now. So first thing we've got is this management RP2040 over here, like Emily was telling us about. It's the Raspberry Pi Pico chip as well. This runs a custom piece of firmware we wrote with Rust and Arctic, or the real-time interrupt-driven concurrency framework. This is connected to the computer through either the USB-C port here, which was useful when debugging with just one target or one cluster manager, but not so much when we're in a lot of them, because we ran 20 in the final production cluster. So this 5-pin JST connector allows us to hook up to a custom USB hub we designed just really easily, and also allows us to provide extra power delivery that USB-C wouldn't work without a bunch of extra external components. This USB host or USB port exposes about 6 serial endpoints. So there's a management API, which is just request response. We can talk directly to the manager. There's logs, so we can see what's going on. And then 4 pass-throughs for the UART or serial back to the USB host, so that we can work out, so you can talk directly with your runners. So from here are the runners. They are all connected through to the management RP2040. And then these are all directly paired with these challenge card connectors, which have challenge cards that go in them. We've also got these status LEDs, so we can check what's going on at a glance with the cluster. And so this was the cluster that we ran in production. You might be able to see the interface in the bottom left, which Tom's going to talk a bit more about later. And yeah, this is just hooked up to my laptop over USB. There's a USB hub there as well, so just plug all these in. Lots of USB device tree stuff going on there. So also, this is what about 50 USB serial devices look plugged in. So this is about half the cluster. This is where we started running into problems with the Linux USB stack, which wasn't properly supporting all these USB devices. So you had to make some quick modifications to fix that as well. So yeah, once the cloud software, which again Tom will talk a bit more about, has some firmware ready on the host, how do we get the code onto the runner and eventually running your code, and how do we do that whole process? So it starts with the host saying, I've got new firmware. So the manager's then going to set up this Flash agent. So this is a little piece of shim code which we'll install onto the runner over SWD. So again, SWD is that debug protocol which you use on ARM to talk directly to the chip and bypass, having to actually have code on the chip. So the shim is going to allow us to call all the ROM routines in RP2040 to actually write to Flash, as well as allowing us to decompress Flash images rather than sending them over byte by byte, which is really efficient in this case. Because we can tunnel, it's going to say, yeah, once it's installed, the Flash agent's going to pop up as ready. And then it's going to allow us to tunnel directly from the host to the runner over UART. And that way we can send the firmware directly from the host, having to avoid the manager mostly. And then from there, your code's going to run a bit. And then eventually it'll hit a breakpoint and stop, and that's what we use as stop condition, as well as timeouts and other stop conditions as well. So yeah, how do we basically not get hacked? We're running untrusted code on the hardware, and what we want to do is sandbox this microcontroller. So in this case, sandboxing for us looks like we don't want runners to be able to steal code off other runners or talk to them at all. We want them to remain in complete isolation with their runner and their challenge card peer. Just to make sure that there's nothing going on there between them, so you can't steal a flag from someone else, for example. We also want to make sure that once we tear down someone's job on the runner and it starts back up again, we want to make sure that the code or the challenge remains functional. So for this, we could just try not running untrusted code, which it's a good way, but the problem is it's slow because we probably end up using some sort of DSL or custom DSL or Lua or MicroPython or something like that with a whole bunch of our own drivers. But at that point, we might as well just emulate it, and it's no fun. And that way, we also lose out on all the embedded stuff that you get, like the low-level PIO access. And that way, we might as well just emulate it in the end. So instead, we're going to implement a bunch of protection. So these are just a few of the ones we implemented. So we've got time limiting because your code shouldn't need enough time to mine a Bitcoin. We want to, run it nice and quickly. We want to make sure there's resources there for other people to come and run their code on. We also have no connections between runners. So originally in the design process, we were thinking to just use a multi-drop SWD bus. So that meaning everything's hooked all up together. Problem with that is someone could potentially send messages on SWD and start programming and probing other microcontrollers, which we really don't want. And so the way we do this is just by having all of our connections only directly between the manager and each runner, and then the manager serves as like a little switch there, essentially. We've also got no overclocking. So we implement this by constantly polling over SWD each runner, just checking that the registers aren't set in that way, so that it's running at a reasonable clock speed. Because we're more concerned about the overheating and the long-term effect on the chip here, because you overheat the chip, the transistors start to break down, and the chip becomes unreliable. But what could also happen is someone just draws way too much current by, trying to overclock it to 1 gigahertz or something. And that's just going to draw way too much current, and in the end it will end up tripping a fuse, which will immediately take the cluster down, but it's about as good as we can do. We also have periodic health checks, so this just makes sure if we're going to run someone's job, they have a known good working environment. So this worked by, we just uploaded the solve scripts we wrote directly to each of the challenges, like every so often, just to make sure that the environment's still working. And so we have all this cool hardware, so what do we actually end up doing with it? So we built 4 challenges this year. So the first one's IC. This was just an easy challenge where you had to read an I2C EEPROM. This challenge is more about getting people familiar with the environment rather than getting them, accustomed to what a timing attack is or whatever. So there was this one write-up, which is really nice to see. So we'll quickly step through it. So basically the first thing they did here was get an Arduino environment set up and with all the infrastructure going on so that they can upload code to our system. Then they wrote some code to dump the EEPROM. This looks like it's an example piece of code, but it's a piece of code nonetheless that dumps the code off the EEPROM. Then they worked out that I slightly changed the EEPROM, so instead of having all the address lines wired to ground like you're usually meant to, I wired them all high, which changes the address of the chip a bit. And so in this way, the chip, you need to query it on a different address over the I2C bus. And then, so then from there, they just ran the code with that new modification, grabbed all the data, decoded it, and got a flag. And so the next challenge we built was called the door. This is a medium challenge, which was based off Sammy Kamkar's research into Open Sesame, which essentially looked at garage doors and how they have a really insecure password system with their remotes. And so we implemented this thing with hardware logic gates because it was a really interesting use of our infrastructure. It's something we could emulate with some code, but it's a very nice to have like all, propagation delays between gates, things you have to consider if you're trying to run fast enough. Then we also built this other challenge, bird loader. So this is a medium challenge where essentially you've got a password protected bootloader. The idea was you had to perform a timing side channel analysis to look at this constant or this like string compare, which was vulnerable to timing side channel attacks. And it's really nice here because it's something we can simulate on the hardware. It's a really real world attack. And then once you perform that, get the password, you can just run the flag command to get the flag on the bootloader. And so the final challenge we built was called CTF. This is a hard challenge built on the RP2040, where it's called Down Under Cabs, Trains and Ferries is its full name because it uses DesFire, sort of. So the idea is you have to exploit a flaw in the RP2040's RNG, where if you don't have an external crystal, the RNG always just reads 0. And so from this you then exploit a flaw in the DesFire three-way handshake where if you're pretending to be a card and you know the RNG of the other party or of the reader, you can just bypass it without an encryption key at all. And so with all of that, there are a few ideas which we have for the future, which you might see next year in CTF. So we're looking for more side channel analysis challenges. So maybe next year we'll implement some power ones where you're, say, reading a key out of a secure element through measuring the power draw that it uses, as well as timing analysis, where you're again looking at like string compares or other vulnerable functions like that. Also, we might do some fault injection where either voltage glitching or EMFI. Also some RF challenges where either you're like sending or receiving data on various frequencies. And also maybe some custom ICs, but they're looking a little expensive. So some sponsors might be nice for that. Without further ado, I'll pass on to Tom, who's going to talk more about the infrastructure we built.
Yep, thanks HexF. So I'll mostly be going through our networking service and cloud infrastructure today. So I'll first go through what we wanted to build. So we wanted to have complete automation for our challenge card provisionings and allocation of hardware resources. And just having our organizers assigning challenge cards through Discord DMs is not something that's scalable. The second main feature that we wanted was having login auditability. So basically, which challenge card was allocated to which run, as well as all of the inputs and outputs. And the benefit of this is that we could provide logs to players at the end of each run. We also wanted some rate limiting to protect ourselves from bad actors. Originally, we planned to have geographical redundancy by hosting from 2 separate locations. However, we did scrap this idea in the end since due to shipping costs. So we built a platform called Eevee that runs on top of our Kubernetes challenge platform. So all the state is stored in a persistent MySQL instance, and the messaging architecture was built on top of NATS, which is a lightweight open source messaging service. So one of the most important features was that it supported in-order messaging as well as both broadcast and request and reply patterns. So each API as well as challenge instance has its own message topic, and we can create them and subscribe to them on the fly. And all of the network communications are tunneled through a proxy called traffic, which is our reverse proxy. And in order to not expose NATs over the public internet, we just left an MTLS cell on it and called it a day. The EV platform was made up of 5 separate Rust microservices, which are all independently scalable. And it also makes our infrastructure more resilient, since downtime in one of the services doesn't mean a complete outage of the platform. If you notice the infrastructure running slowly at like some point, it might have been due to me pushing some bad code changes throughout the CTF. So I'll give a brief rundown of each of our services. So the admin service runs the admin panel, which is used to activate and deactivate individual challenge cards. We also use that to take a sneak peek at your submissions throughout the CTF to see how close you all were to solving the challenges. And the front end is like the main entry point for players and where all the code is submitted, as well as like a place where you can view and download your logs from. And the terminal service is like a remote serial console, allowing you to directly interact with the challenge cards by sending and receiving serial data. We have 2 backend services, which are the agent and auditor. So the agent serves as a bridge between the cloud services and the underlying hardware clusters. And this runs on Hexer's laptop and organizes flashing of code and the communication with the hardware challenge managers. And the auditor's main function is to collect all those serial logs and output them into one log file, which you can then download to inspect the output, as well as handling the state of an individual session. So for example, if a challenge card runs over its allocated time limit, we'll immediately send a kill signal from the auditor. So I'll go for a brief sequence diagram of what happens when you submit your challenge. So first we upload it to a cloud storage bucket and return an instance ID to the player. So on the agent, there's a service that continue polls in a loop for challenges in the run queue. And if such challenges exist, it'll be dequeued, and then the agent will proceed with downloading firmware directly from the bucket. So once we flash the firmware and check if everything's all good, we then send a message from the agent to the front end to register the session, and then create the room and set up the auditing and time limits. So while the instance is active, we will continuously stream serial input and output through NAT. And this is all recorded by the auditor. And if the player wants to connect to the terminal, the terminal will just subscribe to the instance topic and relay the messages back to the player. And when the instance times out, or the code finishes running, we'll broadcast a termination message from the auditor, and this will initiate cleanup on every service that was interested in the instance. So that includes closing the TCP connection and also uploading the run log to our bucket. So we are planning to release a blog post with a lot more detail, but we just haven't gotten around to doing that. Okay. So this is like a picture of our UI. I'm not going to play the video for now, but so that's what you would see when you run the log onto the website. And sorry, it's not okay. I'm not sure why it's not going to the next slide. So wait a minute. Sorry, just 1 second. I'm not sure what's going on.
The video is too powerful.
Yep. All right, just okay. Just skip that. So yeah, we'd like to thank some additional people that helped us throughout the building of the hardware challenges. So we'd like to thank Sam, one of our infra gods, for building the front-end UI as well as integrating with the scoreboard. And also Jamie for doing challenge design and validation and like load testing our infrastructure throughout the CTF as well to make sure we could handle all your traffic. And yeah, last but not least, we want to thank all our sponsors for funding our adventure. Yeah, thanks everyone.
Thanks.
What a great talk. We might have time for one, maybe two questions if anyone has them. Look, hit up we've got a question over at the front. We might take that one.
Thanks, guys. What was the most unexpected part about building the hardware challenges? Was there anything you ran into that you thought might stump you and prevent you from running it during the CTF?
I think that would definitely be the shipping times for all of the hardware that we ordered. I think it arrived like the day before the competition, and I spent a good long night assembling it all. But yeah, other than that, probably just a lot of like little bugs in the Rust code was certainly a big challenge for us. That was, yeah, had to be dealt with. Yeah.
Let's thank our speakers one last time. Great talk.